Well, hey, let's continue our quest to understand exponential relationships. So today our essential understanding is to just recognize that some functions model an initial amount. Okay, initial amount is that amount we're starting with. When we're at 0, this is the value we have, and that amount is repeatedly multiplied by the same positive number. Okay, and repeatedly multiply, that does make it look different, and it shows up different in an equation, unlike in a linear relationship. And I'll compare the two in a little bit here. So an exponential function is a function of the form y equals a times b to the x power, and that's what's unique about this. It is my x, or my independent variable, is an exponent in this case, and my y, my dependent variable, is just waiting to see what x is when I substitute that in. A couple key situations: a can't equal 0, so we can't start at 0, and b, the base number, needs to be greater than 0, and b really can't equal 1. Okay, so a couple of details of it, and it doesn't play out. And this is what the graph looks like when we graph exponential relationships. Like the curve, they got a pretty intense curve to them. So suppose all the x values in a table have a common difference. If all the y values have a common difference, then the table represents a linear function. Like if you see something going up by 2 each time, like it's adding 2, or it is subtracting 7 each time. So as you move down the table of values, if you see that there's this constant amount being added or subtracted, then you're looking at a linear function. But if all the y values have a common ratio, okay, then the table represents exponential functions, so a common ratio. And you can see that like in this table right here. So first of all, I'm checking to see that it is going up by 1 each time, so I can check that out. And this is interesting. So I'm going from here to here, and I can see that it is subtracting 2, and I see from here it's more than 2. So this pattern here that's happening is not a subtraction or adding situation. But I can see to go from -1 to -3, it is times 3. And to go from 3 to 9, it is times 3. And from 9 to 27, it is times 3. And it's this multiplication thing that changes this. The multiplication that's happening between each one, and it's nice and consistent, that's telling me that I'm looking at something that is exponential. It is changing exponentially. In fact, look at my value here. It is increasing a lot, and that would cause my graph to curve. And we'll see that in a moment. For b here, y equals 3x. This one's a linear relationship. There's no exponent on this one. Your x value is right next to the 3, the starting point. Okay. So a couple things you're looking for. You're looking for an exponent, or you're looking for that common ratio. If it's being added, it's linear. If it's being multiplied, it's exponential. So go ahead and try it. You press pause on this one. On these two, so for A, it is linear, and your proof that you would use to show it is that it is adding 2 each time. And when you're adding something, when it's changing by adding or subtracting, you're looking at a linear relationship if it's a nice constant change each time. For B here, I can see that my independent variable is an exponent, which is going to tell me that this is an exponential function. Okay, we're going to do some evaluating of exponential functions. So suppose 30 flower beetles, I didn't even know those existed, are left undisturbed, because why would somebody disturb flower beetles, in a warehouse bin, which is where I would expect flower beetles to be. The beetle population doubles each week, so that's important, doubling each week. And here's the function representing it after X weeks. How many beetles will there be after 56 days? So a couple of things I'm recognizing is 30 is my starting point. Notice where the doubling is showing up, okay? The double ended up becoming my base number, and X is my variable that's changing. So after 56 days, okay, so is 56 days representing which value, my Y value or my X value? Now what happens is, remember, it's doubling each week. So the population happens after X weeks. So X weeks is going to be my time. And this value going to be right here is going to be like how many. How many beetles do I have? My X is going to represent weeks. This is just a substitution problem. So 36 days, or is that 56 or 36? Okay, that's 56 days. So I'm going to take my 56 days and divide that by, so 56 days divided by about 4, because, no, 56 days divided by 7, because I want to see, like, well, how many weeks is 56 days? So 56 days divided by 7 is going to be 8. Okay, so 56 days represents 8 weeks. So this is just a substitution problem. So the function of x, or our y value, is going to be the initial 30 times my base of 2 to the 8th power. Okay, so 2 to the 8th power is 256 times 30. And I end up with the function of x is going to be 7,680. Now that's a lot of beetles. So let me look. How many beetles will there be? 7,680 beetles. And I want to get my label in there so I see it all. Why don't you give it a try? Press pause. And remember, it's just a substitution problem. All right, this is what I end up getting. Now I had to recognize that it's after 3 years, but my independent variable is looking at half-year periods, so I had my exponent became 6, because 3 years represents 6 half-year periods. I end up with 14,580 rabbits. And I included my label on that one. Okay, graphing an exponential function. So what is the graph of y equals 3 times 2 to the x power? Make a table of x and y values. And you want to be able to graph these things, so this is a bit of a precision thing. So we're going to plug in 2. So just substitute in for 2 for x's. So this is saying 3 times 2 to the negative 2 power, and we know this negative 2 tells us it's small, so I go ahead and bring it down. So it's 3 over 2 to the negative 2 power, which is 3/4. So I have a point at negative 2 and 3/4. Negative 1, 3 times 2 to the negative 1, same thing. The 2 to the negative 1 goes down to my denominator. And so it's 3 over 2 to the 1, or 1.5. 0, next and easy, because 2 to the 0 power is 1. So 3 times 1 is 3. So I have a point at 0, 3. And I plug in 1, and so that's going to be 6. I plug in 2, so 2 to the second power is 4, so 3 times 4 is 12. So you can see that it's actually growing pretty fast here. Now for graphing something like this, I need to pay attention to see, true, I'm going from negative 2, negative 1, okay, so my interval is going up by 1, but on my y-axis, it's going 3/4, and it's jumping up to 12, so I have to be careful on what values I use on this one. In this case, we went by 1, 2, 3. It looks like we went by 1s because the information's all going to fit on there. That's what my graph looks like. I mean, nice smooth curve. Don't make them choppy. Don't go like line, line, line. Don't do it. It's going to be a nice smooth curve because that's how an exponential relationship looks when it graphs it out. Okay, I want you to try these two. You're going to need to grab some graph paper. Please don't sketch this in your spiral with line paper. Use graph paper so you can see a really good line here. And use a couple of negative options as well, negative x values, so you can see what this is doing. Press pause and give it a try. All right, this is what these graphs are looking like. I ran out the math on the left one just so I can keep track of what all the information is doing. 3 to the negative 2 power is 0.5 over 3 to the second power. So my negative exponent brought it down. I did my division. And notice it does curve. Nice curve graph. And then the one on the right, if you notice, this negative right here, this negative right here is a negative base. So it ends up being that this positive exponent times this positive base times negative initial starting point gives me all negative values for my y, so I need to be careful on graphing this one. This actually is going to curve. It's going to curve. Oh, bad. There it is. There it is. It's going to curve that direction. Awesome. All right, one more thing to look at, graphing in an exponential model. So mapping software uses zooming function, and here's an equation that models what's happening here for the percent of the original area. So the same thing, when I plug in 0 for my exponent, 0.25 to the 0 power is 1. So that means 1 times 100 is 100. So I have a point at 0, 100. And then 0.25 to the first power is 0.25. That times 100 is 25. So I have a coordinate there. I plug in 2. 0.25 squared times 100, I get 6.25. And I keep moving along here. And now this is an about because there's a repetant to it. So I have to do a little bit of rounding. Same here. This is an about because I had to do a little bit of rounding. It either has a repetant or it just keeps going. The equation, or the value does not terminate. Now when I look at my values here, I'm graphing 1, 0, 1, 2, 3, 4, so that's easy. Okay, so not worried about that one. Nice interval of 1. But on this other side, a little bit different here. It's 125, and it looks like it's dropping. And I need to have 100 on my graph, so I might go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 20, 40, 60, 80, 100. Just so I can get everything on there. So I have a point at 0, 100. I have a point at 125. So there's 20, and there's 30, so 25 is going to be right in the middle of it. And then I have a point at 2, 6.25, so that's 10, and 5 is halfway, so right above halfway. 3 is going to be down toward the bottom, and 4 is going to be practically touching. So my graph looks like, oh, not that. Looks like this. Yes. And that's why I really want to encourage you to use pencil for this kind of stuff. So take a look at it. Speaking of pencils, I'm going to go shove one up my nose and see if I can smell the factory it was made in.